Hey there, chemists. We've been talking about properties of solutions, and today we're going to wrap up this unit and look at how solutes change a solution's freezing point and also its boiling point. This results in a change in the temperature at which a solution will freeze or boil. So to look at this qualitatively, first I want to look at a phase diagram, which remember is a plot of pressure versus temperature. This is a unary phase diagram just for a single component system. And you remember what this looks like from earlier in the semester. We have a graph that's broken up into essentially three sections for solid and liquid and gas, showing where something is a solid, where it is a liquid, and where it is a gas. Remember, it depends on both the pressure and the temperature, not just temperature. And last time we learned that solutions have a lower vapor pressure. Solutions have a lower vapor pressure. This is for a non-volatile solute like salt or sugar, something that's a solid that doesn't vaporize very easily. The picture is different for things like liquid solutes. We talked about that last time. So today we're just talking about solid non-volatile solutes. And as a result of the lower vapor pressure, you'll see that this translates into a lower freezing point, I'll say TF, and higher boiling point, TB. And I'm going to use this phase diagram to show why. So here's our template for a pure solvent, let's say water. Now, if solutions have a lower vapor pressure, how does that change the phase diagram? Well, you get what looks like this in the phase diagram. I'm going to show a dotted line to symbolize the solution as opposed to the pure solvent. I'll actually label that. Here's our solution, the mixture, whereas this is our pure solvent. And this shows us qualitatively how our changes in temperature for boiling and freezing will change. So remember, to figure that out, we can draw a line at some pressure. I'm going to pick just 1 atmosphere and draw just a horizontal line where that intersects this phase diagram. So let's do that actually. Let's just draw a straight up solid line right across, crossing through everything. There's our line. And where this intersects the solid liquid boundary and the liquid gas boundary, in other words, right there and right there for the pure solvent, the solid line on your notes, well, that shows us where the boiling point and freezing point irrespectively are. Here's our freezing point for the pure solvent. Here's our boiling point for the pure solvent. And look at how it's different for where it intersects our new dotted lines. So here it's hitting the solution at a lower temperature for freezing and a higher temperature for boiling. So TF and TB have changed. So because of the lower vapor pressure, which, as we talked about last time, is a result of favorable interactions between the solute and the solvent, so they want to stay mixed, they want to stay combined, we see a lower vapor pressure. So these two lines are lower down. There's changes we could talk about for the solid gas barrier as well, but I just want to go from solid to liquid and liquid to gas, just focus on those, because that's what we see in front of us in a laboratory typically. And as a result, the temperature at which you change phase is different. So we have a delta TF and a delta TB, where we compare the solutions to their pure solvents. Now, quantitatively, it's based on this equation. The absolute value of the difference in temperature for freezing and boiling is based on I, capital K, and italicized M. And let me show you what those things mean. I is called the Vent-Hoff factor, which is the number of dissociated particles. We'll explain that in a second when we look at some examples. Capital K is called the molal constant. It's really just used for this equation. It's based on what the solvent is. And there's one for boiling, KB, and there's one for freezing, KF. For water, it's 0.512 degrees Celsius per molal. Remember, this is molality, lowercase italicized m. And KF for water is 1.86 degrees Celsius per molal. Again, these are just for H2O. Every solvent has its own boiling point constant and freezing point constant that work in this equation. And then italicized m, the last part of that equation is the molality. So that's really why we use molality in this unit, because it shows up in this freezing point and boiling point change. It's similar to molarity, but it's not exactly the same. It's based on mass of solvent, not volume of solution. Okay, so let's look at some examples, starting with just what's up with this Van 't Hoff factor. How is it different for different types of non-volatile solutes? So here's 4 examples of solutes. How do we figure out the Van 't Hoff factor for each of these? Well, think about how a substance like sodium chloride dissociates when it goes into a solution of salt water. NaCl dissociates into 1 sodium ion and 1 chloride ion. There's 1 particle plus 1 more particle, so the Van 't Hoff factor is 2. It's just the number of particles you get, in this case the number of ions, when a compound dissociates in solution, if it dissociates. So hit pause for just a few seconds and see if you can figure out what the Van 't Hoff factor would be for each of these other 3 solutes. How do they dissociate? How many particles do you get? Okay, let's see how you did. For B, potassium phosphate will dissociate into 3 potassium ions and 1 PO43 minus, 1 phosphate ion. So you add those up, you get 4. So there's a 4-to-1 factor of, for every 1 potassium phosphate, I get 4 particles dissociate in solution, and they contribute to that boiling or freezing point change of a solution. The next one, this is the molecular formula of glucose, so it's molecular. This doesn't dissociate. Now that doesn't mean I is 0, it just means I is 1. For every 1 glucose molecule, I get 1 particle. They dissolve, but they don't dissociate. Remember, those 2 words don't mean the same thing. If something dissolves, it goes into solution and adopts the phase of the solvent. So sugar water looks liquid, like the solvent. But the sugar molecules don't dissociate. I don't break these apart into carbon, hydrogen, and oxygen atoms. It stays as individual molecules. The last one does dissociate. Calcium chloride gives me 1 calcium ion and 2 chloride ions for a total of 3 particles for every 1 calcium chloride. That's how the Van 't Hoff factor works, and that's how it plays into the equation. Now let's use that equation and solve for some changes in boiling point and freezing point for a couple of solutions. 17 says, what's the molar mass of glucose, which is covalent, if this much glucose dissolves in this mass of water and the solution boils just a little bit higher than it should, 0.34. This is a perfect example of how we use this property of solutions. We often measure the change in temperature at which it changes phase, and then we can use that to indirectly find out something about the solute, in this case, a molar mass. So let me actually start with the equation we have up above, absolute value of delta T, in this case delta TB, because we're talking boiling, is equal to Van 't Hoff factor times KB times molality. Now, I want to plug in everything we know and try to extract what we don't know. We actually know the delta T, it's this 0.34. We also know I, because it's covalent, that means I is going to be 1. And since the solvent is water, we know KB. So we don't know molality, but we know a lot of what goes into the molality. The molality, remember, is, I'll just put it in a side note here, molality is the mass of the, sorry, not the mass, the moles of the solute divided by the kilograms of the solvent. We actually know the kilograms of the solvent. We don't know the moles of the solute, but we know the mass of the solute, and we're trying to find the molar mass, which is buried in the moles, which is buried in the molality. So I'm going to extract that molar mass right here in this equation. So our delta T is 0.34. Our I is 1. Our Kb, because it's boiling, is 0.512. And then our molality is moles over mass. And moles is mass over molar mass. So I'm actually going to write that like that, and there's our unknown molar mass. Our mass of solute is 18 grams divided by our unknown molar mass of this solute. And then the kilograms of solvent, well, if I read the question back up here, it says it's 150 grams, so that's 0.1500 kilograms, and then we can use this to solve for our molar mass. You take out a calculator, you do the math, you get a molar mass of 180 grams per mole, which, if you remember the formula glucose, it is actually C6H12O6. That's just because we happen to know that, and that does match up with what glucose's molar mass is. So if we wanted to, we could actually rearrange this equation and solve for molar mass, but I'll just leave it like that, and remember we can substitute in what we know to get the molar mass each time. So hit pause one more time and see if you can try these last two. 18 asks us to figure out the mass of a solute that goes into a solution to change its freezing point. And 19 is another figure out the molar mass question. Hit pause and see if you can do both of those now. Okay, so let's see how you did. For number 18, they want the mass of this ethylene glycol solute. They tell us what the formula is. They tell us the mass of the solvent, and they tell us the change in freezing point. Ugh, the first thing I notice is that it's in Fahrenheit. We have to change our Fahrenheit into Celsius. So remember the Celsius temperature conversion, we don't use this that often, but it's good to know it, is the Fahrenheit temperature minus 32 and then times 5/9. So if I do that for this, our -10, if I plug that in, you get -23.3 degrees Celsius. That actually is the delta T, because water freezes at 0. So if it's freezing at 23.3 below 0, that's our delta T. So we're going to use the same equation. Absolute value of freezing point change is equal to I, this times Kf, and then times the molality. Our freezing point change is 23.3. I is 1, once again, because it's a covalent compound, so the Van 't Hoff factor is 1. Kf, I look above, is 1.86 degrees Celsius per molal, and then the molality is moles per kilograms of solvent. This time we don't know the mass of the solute, so that's our little unknown, M, divided by the molar mass of the solute. If we add up 2 times 12 for the carbon plus 6 times 1 for the hydrogens plus 2 times 16 for the oxygens, you get 62 grams per mole. That's our molar mass of the solute. So in our molality expression here, I have an unknown M divided by 62, and then the mass of solvent is 10.0 kilograms. So we rearrange and solve, and you get your mass of solute to be 7,770, and that's grams. And then the last one to practice for today is another figuring out of the molar mass of the solute. This time, if you tried this, they gave you a different solvent. Benzene is a different solvent. So it has its own molality freezing point constant. They give us the delta T. I'm going to use the same equation. Absolute value of delta T, in this case F, is equal to I, K, molality. The delta T is given right there, 0.240. I, well, it says it's molecular, so once again, I is just 1. K is given because it's a different solute, 5.12, much bigger than it is for water. And then the molality has the molar mass buried within it. This is just like the one we did 2 problems ago up here. Molality is moles over kilogram. And moles is mass over molar mass. So I'll plug in what I know and leave as a variable what I don't know. We know our mass of solute, it's 15.0. We don't know our molar mass. I'll say MM for the unknown. And we know our mass of solvent. Oh, my apologies, it's not 15 grams of solute. That's the mass of solvent. Careful, it's 0.546 grams of solute. And 15 grams of benzene, which is 0.0150 kilograms of the solvent. One equation, one unknown, solve for the molar mass. You get a molar mass of 777 grams per mole. And that's how we use freezing and boiling point changes of solutions to figure out the properties of typically the solvent or sometimes the solute. We can do this to find what experimental value is for the K. We're actually going to do that in the laboratory. It's commonly used to figure out the molar mass of a solute because the change in freezing point and boiling point depend on just the molality of particles, but not necessarily what the identity of it is, and how many particles you get, what concentration it has is just based on its molar mass, its Van 't Hoff factor, and then what that freezing point or boiling point change is. Okay, thanks for watching.